Alrighty, hello everybody. We're back here for another lecture. We're doing lecture 11 today, which is going to be talking about how enzymes work. This one should be pretty short. It's not as complex as lecture 12, I think, which is talking about Michaelis-Menten kinetics, but still something to keep in mind because it can show up on the exam. It often does show up on the exam when it comes to how these things work. So let's go ahead and get into it. Also, I think this is the first lecture right after your exam, so congratulations on being done with the first exam. Hopefully it went well. If it didn't, you got I think like three-ish more right to get through. So hopefully you can at least pull it back for one of them or two couple of them. And so start with this, right? So if you know your OChem, this should be really simple. If you don't, it's okay. You know, it takes a bit of time. You'll get it once you take a look at it. Idea is right that we start with some reactant that's lower in energy. We want to get to some product, right? That's lower in energy. I'm sorry, some reactant that's higher in energy than the product, but we want to get to a product that's lower in energy, right? So this in this case it's an SN2 reaction, but just be aware that this is what they're looking for. And then to get here, we have to go through some transition state, right? And the transition state is much higher in energy. And basically what all this is saying is that you need energy to complete a reaction, right? That's all this is saying. I want to stress this. We have two different types of constants that tell us about spontaneous and speed, spontaneity and speed. Delta G, right? This is not actually, but this is not the same thing. It does depend on delta G, but so we have delta G, right, for spontaneity, and then we have K for rate, right? So this is rate, this is spontaneity. So they don't mean the same thing. This does influence this, but they're not the same thing, right? So what this is saying is, right, that the rate of the reaction, so K, right, so rate of the reaction, double arrow, is dependent on G, which is that. And that'll make sense in a second, but and you know this height, the height of the activation barrier, so like how tall this is, right, depends on how the substrate fits in the enzyme, so the alignment of the reacting groups in a favorable orientation for the enzyme, right? And then it depends on like the energy needed to form the bonds. So bonds that are stronger, right, will take more energy to break. They're not as strong, they require less, right? So catalysts, aka enzymes, they work by lowering this delta G plus plus. So like they take this hill and they make it lower. So they make it like this instead, right? That's the main gist there. So you can see here delta G plus plus, right? Yeah. So how do we speed them up? Kinetic energy. So if we add heat to a reaction, right, we can get over this barrier much quicker, right? Because heat is energy, right? We can also stabilize the transition state. So stabilize this, right? So make this lower in energy, right? Make this lower G plus, right? That would make this easier to overcome with less energy, right? So you need less energy to overcome that barrier, right? Or you can use coupling, right? So coupling is like using ATP to overcome things. Like for example, things that are not spontaneous. If you couple it with a reaction that is spontaneous, the whole total reaction could become spontaneous. The idea here is that like catalysts, right? Enzymes, biological catalysts, they're not consumed or changed in the reaction, right? They're just kind of there. They also don't don't alter the overall delta G naught. So that means from the energy of the substrate to the energy of the product, that change doesn't change. The energy drop here from here to here is still the same. What it does change is this. It changes the energy required to go from here to up here. So instead of going from there to there, it now goes from here to here, right? So it dropped down to this point here, to this blue here, right? So we went from here to down here, right? So we changed the delta G plus plus, which is what that is, right? Right. This is just a nice little slide. I don't think it's really that important. Just know that they are biological catalysts, right? They do a lot of things. The rate of catalyzed reactions is just so much faster. It's like not a million, it's 100,000 to like 10 million times faster, right? They generally work under like neutral-ish conditions, right? Neutral pH, 1 atm, and they have very high specificity. So chiral, like, so the thing is, right, amino acids, right, proteins, right, are made of amino acids, and amino acids are chiral, right? And they will recognize chiral molecules. So like they are very specific for certain things, right? So like they'll only be able to identify certain types of proteins or substrates. So all your proteins, right, they're made of L amino acids. Did I say that right? Yes, I did. They're made of L amino acids, right? So they will have very specific substrates, right? So they can't, and they're better at identifying other L amino acids, generally speaking, right? They aren't very good at identifying D amino acids, right? So that's something to keep in mind. Similarly, the L amino acids, they're good at identifying D sugars, generally speaking, if I remember correctly. So they don't really identify L sugars very much, right? So that slight enantiomeric difference, right, makes it very actually do its job. So a lot of like antibiotics, right? Um, if you want to make an antibiotic that's undetectable, right, you probably want to use L amino acids, right, if you're making a peptide chain, because usually antibiotics that are D amino acids that use D amino acids can be identified by proteases within a bacteria, right? The rest of this isn't really that important. I think high selectivity and very few side reactions is the main thing there. A couple of things that you should know, just memorize these. So the active site is where any reaction takes place, right? In an enzyme, the substrate is the thing that the enzyme binds to and turns into a product. A cofactor is usually just some sort of extra part required to actually help with the enzyme's activity. Usually includes, like, it usually is an inorganic ion. So like the DNA polymerase, for example, is one that uses magnesium. But yeah, there's other things. You can use zinc, you can use sodium, you can use iron, you can use whatever, right? Um, Also called coenzymes. But coenzymes is a little bit more broad. Coenzymes usually refers to organic molecules specifically, so they have to include carbon chains. So NAD plus, FMN, vitamins like B12, B9, all these, B2, B3, B5. These are all vitamins that are made of different carbon chains and carbon structures, right? And so those are also required. But the difference between cofactor and coenzyme is cofactor is usually a little bit more specific and it encompasses metals, while coenzyme is a lot more broad and encompasses, um, generally speaking, I would say both cofactors and coenzymes, or sorry, cofactors and like organic molecules. But in this case, it seems like they want you to specifically focus on organic molecules. Um, so I would just focus on that. So holoenzymes is usually it's like the whole enzyme. So the enzyme plus its cofactors, right? So enzyme plus cofactor, and then apoenzyme is the enzyme not bound to the cofactor or coenzyme, right? It could be a coenzyme here, by the way, too. It could be a coenzyme. Not it doesn't have to be a cofactor, but it could be a coenzyme. Okay, so when you name enzymes, if it has ace at the end of it, probably an enzyme. So DNA polymerase. Let's see here. Like NADH reductase, or I'm trying to think of good examples now. Pyruvate dehydrogenase, glyceraldehyde 3-phosphate dehydrogenase, G3P dehydrogenase, right? These are all. I think that's one of them. You see, I've forgotten my biochem now, but yeah. Anyways, so those are some examples. So these are, you should memorize these. Hopefully it's kind of intuitive, right? I mean, like, if there's an oxidation or reduction reaction, oxidoreductase. If there's a transferase. If there's an isomerization, so same formula but different connectivity, isomerase. If there is a chain building, well, this is a bit different, but like I guess you can think of like building a polymer, right? A polymer is multiple things connected together, right? Or multiple of the same thing connected together, right? So polymerase, right? Polymerase, right? Okay, reaction rates. So I told you, right, that delta G does not equal K. And this is what this says. They are not equal. They are proportional. So K is proportional to delta G plus plus. Right? They are not equal. Right? So the if I had this reaction coordinate diagram, right? Delta G naught tells you from here to here what is the difference. This, right, is looking at this height here. That is what that's looking at, right? Very different things, right? Because we're going from products and reactions. So products minus reactants, right, gives you the delta G naught, but we're just delta G. Delta G plus plus tells you how much energy is required to go from this point here to this point up here. Ooh, my voice kills me whenever I start talking for a long time. Okay, so you don't have to know this equation. Just know that the how fast the reaction is proportional to how big this barrier is, right? So if I lower this barrier, if I make it smaller like that, this delta G naught goes down, right? And so this actually becomes larger because it's a negative to the power of a negative number for E. And that basically turns it into like a fraction. So 1 over E to the power of whatever, right? So like, so power of whatever X is, right? And if I make X smaller, it becomes a smaller number on the denominator, right? And 1 divided by whatever this number is times this term here is a bigger number. But I would just say that know that K and delta G are not, or delta G are not the same, because they will ask about that. So yeah, lower activation energy, faster reaction. This is just a little, I guess this is just an interesting little schematic of how this works. For the uncatalyzed reaction, you just go from substrate to product, right? It's kind of slow, pretty dang slow. This delta G not a delta G plus plus. I keep saying not. Delta G plus plus uncat is friggin' massive. It's like all the way from here to here, right? For the catalyzed reaction, right, you go from enzyme plus substrate to enzyme substrate complex to enzyme product complex to enzyme plus product, right? Got this stuff, right? And the K cat, right, you take this delta G not delta, oh my god, delta G plus plus cat, which is so much smaller from here to here, right? Significantly smaller, right? It's like what, in this case it's like what, four times smaller. So this number would be like way low. And so you'd have the 1 over e to the x, right? Where this x is way lower. Well, actually, well, basically like right? So this number is lower, so that means e is lower, right? And so that would mean that 1 divided by this b equals big number, right? Big number. You probably won't have to do this math exactly, but just keep this in mind. Yeah, so same idea here. Because delta G is in the exponent, a small difference is a big change. That's what I was saying here, right, with this whole math stuff here. This math, don't really need to know it. I guess just know it if you want to, but I wouldn't say you have to know it to do well in the class. Right, so enzymes, specific substrates, right? And they orient substrates in a specific way, right? They increase the probability of a reaction occurring, right? Because they put two things in contact that are meant to be in contact to cause a reaction. And also, substrate specificity, they only bind certain substrates because they're chiral, right? Other part is like shape complementarity. So like enzymes are built in a specific way to bind certain substrates. Also part of the no side reactions, right? So like the active site of any given enzyme, like the active site of like pyruvate dehydrogenase, for example, will be very specific to pyruvate. It would not take any other molecule, right? Yeah, so induced fit, basically this idea that when you bind, so like when you initiate and change in the enzyme complex, that will cause it to cause a tighter fit around the substrate, basically. Basically, binding of substrate leads to better binding of that substrate because the enzyme changes conformational shape, changes its shape, right? And then that shape tightly binds that substrate. Yeah, so this idea that like catalysis only occurs when all substrates are present, right? So maybe the binding of the initial substrate, right, opens a pocket for another substrate to come in. So like maybe the binding of this, like for example, like hexokinase, for example, right? So the first step of glycolysis, right, has a binding pocket for glucose, right, and also a binding pocket for ATP. It might be the case that in order to open the binding pocket for ATP, glucose needs to bind first, right? This is just a nice little image of how like enzymes kind of work. Um, so let's just imagine, right, that you have a metal stick, right, and you try and bend the stick. Um, Takes a lot of energy to bend the stick, right? I mean, I don't think I could bend a metal stick if it's like 4 inches thick, right? No chance. Or like 4 inches, 5 inches in diameter. It's pretty dang hard, right? So I can't bend this stick, right? So it takes me a lot of energy to get up to here, right? A ton of energy, right? I might even, I mean, if I put enough strength into it, I'll break it, but it takes a ton to get up there, right? Eventually it'll start to bend and I'll be able to break it, but pretty dang hard. Now, if I take a compressor, right, and I stick the stick under the compressor and I smash it, right, like this enzyme, right, it makes it a lot easier, right, to bend and break the stick, right? So initially we'll have like no products because all the enzyme will just suck up the stick, right, and none of it will turn to product. But eventually, right, we'll go from having to go all the way up here to being down here because the transition state, right, the enzyme, the compressor, right, has been able to compress this stick and make it much easier to break, right? The idea here is that enzymes lower this activation barrier, so this delta G plus plus, right, to make it far more doable and far faster for these reactions to happen, right? Because remember, delta G plus plus is proportional to K cat. This is a nice thing to keep in mind. So acid-base catalysis, so a lot of enzymes use acid-base properties to actually stabilize substrates and do different things. Um, so I guess an example of this is, so keep in mind, right? So the acidic and basic groups, what are they? Acidic, we've got aspartate and glutamates of D and E, right? 3.6, 4.2 pKa's around. For the basic groups, we've got arginine, lysine, I guess histidine too, it's like 6.1, 12.1, and 10.7, right? Those pKa's kind of mix the order around there. Histidine 6.1, lysine's 10.7, arginine's about 12.1, right? So they accept H pluses and they donate H pluses to stabilize these species, right? So here's an example of chymotrypsin, like a serine protease. It's called a serine protease because it uses serine, right? So what happens in this reaction is very basic OChem, right? These electrons grab this H, turns this into a minus charged oxygen, right? And that minus charged oxygen is able to attack this carbonyl because this carbonyl, right, is pulling electron density this way, right? Which ends up breaking off this N bond here. And so you release this, right? You release this, and then this is now stuck to the enzyme, right? So you should have in mind, I guess a couple things. So obviously enzymes use amino acid residues, right? Because they are proteins, right? So, and they use things as H plus donors and acceptors. So the donors, try and think about what they are. Acceptors, what are they? I mentioned them above, right? So the active site, right, tends to provide special environments. So remember that the environment influences the pKr of the side chains of these amino acids, right? So if you add like more basic amino acids, right, you'll probably make the make that area more basic, right? So you probably make the why am I blanking right now? Make that area where those side chains are at more basic, right? If you have more acidic amino acids, you might make those that area more acidic, right? And that might be important for the function of the enzyme, right? So I think the other thing to just keep in mind, right, is like these are all the ends, like the amino acids that you'll see. So like I can think of like quite a couple of proteins probably that use these. Maybe not for cysteine, but like like most of the like most acid base catalysis enzymes use glutamate and aspartate. Tyrosine receptor tyrosine kinases. So like one of those GPCR cascades that you've seen before. You've heard probably about in like Bio 200. You'll go in depth on those in 442 hopefully. Serine proteases, right? Hemoglobin, right, for histidine. Um, try and remember what these do, and try to remember the forms, right? So remember the acidic form, right, of these guys, and the basic form, right? So like usually for O's, right? So for any O group, right, the acidic form is neutral, basic form is negative. For N's, right, it's positive in acidic form, neutral in basic form. For SH, it's neutral in acidic form, negative in basic. For this N here, also positive and acidic, neutral and basic. So you can kind of see the pattern here, right? So yeah, so this idea of covalent catalysis, right, is just this idea that the enzyme forms a covalent bond between the substrate and the enzyme. Um, that's all there is to it. It doesn't stay for long, where transient intermediate means that it disappears rather quickly, but there is a covalent bond formed. And just a review of nucleophiles and electrophiles. Remember, nucleophile, electron rich, electrophile, electron poor. So these carbonyl groups, right, because they have electronegativity, pulling the carbon's electrons away, right? This is a good electrophile. O minus, right, good nucleophile. S minus, good nucleophile. Carbanions are really annoyed, so they are obviously good nucleophiles. Anything with lone pairs, right, generally a good nucleophile. Anything that has a plus charge, anything with a partial positive on it from electronegativity, also a good electrophile, right? And here is actually, I believe this is an example of, what is this? I don't remember what enzyme this is. I probably 2-phosphoglycerate. Oh yeah. So this is step 8 in glycolysis, I want to say. I think enolase, if I remember correctly, which you'll learn about. So metal catalysis, right? 1/3 of all enzymes require metals, like we said. Magnesium, zinc, sodium, stuff like that. They help with their cofactors, right? They help do all these things. They bind and stabilize the substrates, right? Um, yeah, I mean, I would just try and keep these in mind. So this is an example of a mechanism of how this works, right? So you can see how these magnesium ions, right, are helping to stabilize the electrons on these O's, right? You can also see how this lysine, right, acts as a base to pull off this hydrogen, so that you can basically form like this double bond intermediate right here, right? And then you can also see, how uh, that results in like this other reaction where these electrons come back, they come back here, right? And then this basically this bond here gets kicked off as water, basically, right? So all this to say that all these different parts, right, are required to keep these enzymes functioning, right? Other than that, that's the end of this lecture. Relatively short, um, but I think the next couple will be a little longer probably because they're a little bit more information. But who knows? Maybe I'll be able to get through those quickly as well. But yeah, hopefully this was helpful. If it was, great. If it wasn't, come ask me questions at the IC. But yeah, have a good one, guys.